Hi, today we're going to be talking about chemical kinetics. And we're going to start off by talking about reaction rates. Now, just so you know, chemical kinetics is the fancy word that talks about reaction rates and the factors that affect them. Okay? So it's a study of reaction rates and the factors that affect them. And keep in mind that all rates are ratios. All right? Think of rates like the speed of a car in miles per hour. So that per part means that you're taking something that changes and dividing it by a change in time. Now, reaction rates are specifically looking at how fast a chemical reaction takes place. And it is usually a decrease in the reactant concentration or the increase in the product concentration per unit of time as a reaction proceeds. So usually it's something that's easy something to measure, okay? So it's basically a change on how much reactant you have, how fast a reactant gets used up, or it could talk about how fast a product is being produced. All right. So keep in mind that reaction rates are measured as average rates, not instantaneous. An average rate is the total change in a measured property, usually concentration of either the reactant or the product, divided by the total time for the reaction to reach completion. In other words, they're not instantaneous rates. If you're looking at a chemical reaction, let's say a campfire, okay, the combustion of a campfire, and you look at, well, how much wood gets burned up in how much time? If you look at any one particular moment, you're going to have different speeds of that reaction. Think of a campfire. You can tell how fast a campfire is burning by how large the flames are. The larger the flames, the faster the reaction. So when you get a campfire going, when it first starts, it probably starts off rather slowly. Then you get a big fire going, and if you don't keep adding fuel, after a while, the fire starts dying down. In other words, it slows down, and then the flames eventually disappear, and all you have are like hot coals, and then eventually even those will burn out. So the reaction starts off going fast and then kind of slows down as time goes on. Well, instantaneous reaction rates are actually rather hard to measure, okay? Much better just to measure, well, how much wood was burned and how much time did the entire thing take. That gives you the average rate. All right, so in the formula here, delta represents change, okay? Keep that in mind, that triangle indicates a change in something. And then the brackets around the X represent the concentration of either reactant or product, and T represents time. So as the reaction proceeds, the instantaneous reaction rates usually change, most often decreasing, like I mentioned. Calculating the average rate is the best way to determine the overall rate of the reaction. And it's most often measured in molarity per second, or basically how fast the concentration changes per second. But don't worry, I'm not really going to have you guys calculate this. That's not as important. It's much more important to understand, instead of measuring reaction rates, what factors can affect them, okay? Now, to understand all of that, it's very important to understand what actually goes on when a chemical reaction occurs. And there is something that helps explain what's going on, and it is known as the collision theory or the collision model. And it basically says that reactant particles must physically collide with each other. All right, so if you have one reactant particle, another reactant particle, they're flying around, they're moving around, they have to bump into each other. And with a certain degree of kinetic energy, i.e., they have to hit each other fast enough for a reaction to occur. All right, and as I said, this concept of explaining how reactions actually occur is known as the collision theory. And particles basically need to hit each other hard enough and with the right orientation to break their bonds. That's the trick, okay? So when you have like two molecules, they're hitting each other. If they're not moving very fast, they might hit each other, bounce off, nothing happens. But if they hit hard enough, that provides the energy, the bond energy. That fast movement provides the bond energy to break the old bonds. Remember, bond energy is the amount of energy required to break bonds. So the old bonds will break, and then new bonds will form. And the new bonds are more stable than when they're separated, and therefore they release energy. All right, just like we learned about before. So basically, this is the collision theory. And if the particles do not have enough kinetic energy when they collide, then the reaction does not occur. Now, how much energy is required? That's known as the activation energy. This is the minimum energy required in order to cause a chemical reaction, okay? And in endothermic reactions, the system ends up with more energy than they started with, all right? Started with more energy than it started with. And with an exothermic one, it's the opposite that occurs. And in order to illustrate this, we use diagrams such as these, all right? Now, if you can see, let me get the pointer up here. Now, as you can see, the y-axis represents the total amount of energy in the system. And this, the x-axis, basically represents time as the reaction progresses. So, a system will have a certain amount of energy, whatever its baseline energy, but every reaction needs to have energy added to it in order for it to react. All right? And this initial increase going up, that is the energy added to meet the activation energy requirement. So you need to provide enough energy, it needs to be all the way up here for those initial bonds to break. And once they break, then energy is released. And as it's released, the energy in the system goes down, and you end up with whatever products you have. Now, there are two ways of looking at this. Either you have an endothermic or an exothermic. Now, let me do some rough drawings here. Now, in this one, I don't know if you guys can make this out. This, where the reactants, are higher up than the products, this represents an exothermic reaction, where you put in some energy, but more is released, just like we learned in the last activities. And then this represents an endothermic, where you put in a lot of energy, but only a little is released. And you end up with products that are higher than the reactants, okay? So that is that. Now, that's how you can represent a chemical reaction. Next, I want to talk to you about the factors that affect reaction rates, because a lot of chemistry, believe it or not, a lot of chemistry is involved with either trying to speed up a chemical reaction or slow it down. All right, some chemical reactions we want to speed up. If we are trying to get, for example, instead of a slow burn, we're trying to get an explosion, then we want to speed up that chemical reaction. Sometimes we want to slow the reactions down. For example, if you are trying to transport food from point A to point B, all right, you're a trucking company or you are a food company that's trying to feed people far away from where the food is made, then remember, rotting is actually a term for a bunch of chemical reactions that occur that makes the food no longer palatable for human beings, no longer edible. And so you want to do, if you're a food company, you want to do what you can to slow those chemical reactions down so that the food does not rot as fast as it normally would. And that allows the food to get from where it's grown or made to people hundreds, if not thousands of miles away that need to eat it. All right. So a lot of time and effort out there in industries and so forth go into this concept of chemical kinetics and trying to find factors, trying to find things either speed reactions up or slow them down. All right. Now, basically, when it comes down to it, any condition that increases either the number or intensity of collisions or both will increase reaction rates. Now, in order to help illustrate this, I'm going to use an analogy. Now, I am in no way, shape, or form advocating that you do anything like this, okay? I want to make sure that's perfectly clear. I am not trying to advocate any type of hurting of children, okay? But that said, a good analogy is this. Imagine that you have a bunch of little kindergartners, okay? Little kindergarten kids. And you take them and put them into a room like the gym, all right? Like our old gym. You put them into a room. You pad the walls with padding and lay down the gymnastics pads on the ground and everything. And then you take the kids and you blindfold them, all right? And let's say you start off with a classroom like 30 kids, and you put them in there and you tell them to run around blindfolded. Every time that they hit each other hard enough in the head for at least one of them to start crying, that represents a chemical reaction, okay? Again, I'm not advocating this, but I think this is something that's going to stick in your head. So if we want the reaction to go faster, we want to either have more collisions or for them to hit each other harder in order to get more crying, as it were. And that equates to a faster reaction rate. Now, one thing we can do is we can increase the concentration, all right? In other words, if we have more kids in there in the same amount of area, that's going to mean a better chance of them bunking heads, a better chance of a collision. And it increases the number of collision. But also, this can be done one of two ways. One, you could just put more reactants in there. Or two, what if you took those same original 30 kids and you put them in a smaller room, like a normal classroom? All right, you're not adding more kids. All you're doing is decreasing the area that they're in, and that will increase the volume. That increases the concentration. Now, what this equates to is, as you see here, if the reactants are gases, well, if you take a gas and you increase the pressure, it squeezes it down to a smaller volume, right? Pressure goes up, volume goes down, and therefore by squeezing it into a smaller volume, you have the same number of gas particles, but in a smaller area. Therefore, that increases the concentration and thus increases reaction rates. All right, so that's one thing you can do, increase the concentration. Now, another thing you can do is increasing the temperature. All right, now remember, temperature, we learned, is how fast the particles are moving. All right, how much energy they have, how much kinetic energy. So the higher the temperatures, the higher the speeds they're going to have when they collide. All right, and therefore the more high energy collisions, the more collisions that break bonds, and the faster the reaction. So the higher the temperature, the faster they're going. So again, going back to the analogy of the kids, what if you went and gave all of them, I don't know, a Frappuccino, all right, something with lots and lots of sugar and lots of caffeine, and just get them all buzzed up? They're going to be running around much faster, aren't they? Boom, that's like increasing the temperature. Much more likely for them to break, to bonk their heads and to start crying, all right? So faster moving particles have enough kinetic energy to meet the activation energy requirements for the reaction. All right. Another factor is increasing the surface area. Now, again, imagine the little kids are in there and they start clumping up together. All right, they start, pathetically holding on to each other, hugging each other, and so forth. And if they're hugging each other, they're not going to be bonking heads, are they? So what can you do? Well, increasing the surface area. All right, we've done a lot of demonstrations on this where if you increase the surface area, you make the reaction go faster. Whether it is if you're trying to light a campfire, you don't just start lighting a big log. You have to start off with smaller things like newspaper or kindling. Or if you remember back when we did like the jet engine demonstration, with the big water bottle. And we took the ethanol and we put it in there and it went boom, okay? And it burned a lot faster, much faster than if you just put ethanol on flat and keeping it together. It burns much slower. So increasing the surface area, if you increase surface area, reaction rates will occur. And why does this happen? Well, the more surface area allows more collisions. All right. If you're talking about the collisions between oxygen and a fuel, the more surface area the fuel has, that allows more oxygen molecules to get added in order to collide. All right. That's why, for example, the wick on a candle, we learned it draws the wax up and exposes it to more oxygen, allows more oxygen to get added. That is increasing the surface area, and therefore it speeds up the chemical reaction. Now, the last thing is the presence of a catalyst. All right. Now, catalysts are chemicals, they're substances, they're things that speed up a reaction without being consumed. All right. They themselves are not being consumed. Now, I want you to think of another analogy for this. On this one, let's say for whatever reason you wanted to build a birdhouse, all right? And you get all of the materials together. You get some wood, you get some nails, maybe some glue, and all the pieces, okay? And one way that you are going to try to build it, but let's say, the only tool that you have to build it is a big rock. Now, could you build a birdhouse if you have all the materials and all you have is a rock? Yeah, I mean, you could. It wouldn't be easy and it would take a long time. All right, I guess you can take the wood and break it with the rock and put it into the right size, maybe hammer some nails in with the rock, so forth and so on. So you can do it. You would end up with something that probably no self-respecting bird would ever want to live in, but it would still be technically a birdhouse. So that would be just by itself. But now, consider you trying to build a birdhouse in a well-supplied workbench, all right, with all sorts of tools. And you have power saws, and you have hammers, and you have vices, and all these sort of stuff. Now, these tools, they don't get used up in the process, do they? When you're all done building the birdhouse, you still have a hammer, all right? You still have a vise. But now you build the birdhouse faster. It's easier. It takes less energy in order to build the birdhouse, and you could build a lot of them in the same amount of time that it would take you to probably build one with just a rock. That's what catalysts do. They increase reaction rates, all right, but are not consumed. And the way they do it is they actually change the reaction's pathway. Technically, what they do is they lower the amount of activation energy needed. They make it so that the particles don't have to hit as hard. Most of the time, they do it by orienting them in just the right way so that when they do collide, they hit it just right that it helps break the bonds. It's kind of like if you're trying to break a brick or a rock in half and you got a hammer and a chisel, if you hit, here or here or here, nothing happens. But if you hit in just the right place with that hammer and chisel, boom, the whole thing just splits in half. All right? That's what enzymes do. They make it so that when they hit together, they hit in just the right place, and it makes it so much easier for the reaction to take place. All right. Now, there are three types. There are three types of catalysts, and I want you guys, when there's a little demonstration on the three basic types that I want you to see, but there are homogeneous, heterogeneous, and enzymes. And homogeneous catalysts, these are the same state of matter as the primary reactant. Heterogeneous catalysts, those are a different state of matter as a primary reactant. And enzymes, those are catalysts that occur with biological reactions. Now, just so you know, as I said, the catalysts change a reaction's pathway. Let's say the red represents the normal uncatalyzed reaction, which means that you need all the way up here this much energy in order for it to occur. Now, a catalyzed reaction, if you notice, they still start off at exactly the same energy for the reactants and exactly the same energy for the products. But the difference is here that the catalyzed reaction pathway requires less activation energy. That's why they go faster, okay? That's why they go faster. And as I said, enzymes, they catalyze biological reactions, anything in a living organism. Now, enzymes are very, very important. Think of all of the chemical reactions that take place in our bodies. If it wasn't for enzymes, all of those chemical reactions, those billions and billions of them that occur every second, would require too much energy. Without enzymes, we would literally not have enough time in the day to cram ourselves full of calories in order to survive. All right? So we are able, with enzymes, to do the same chemical reactions, but requiring less energy. Therefore, we need less food in order to survive as an organism. All right? And an example of an enzyme, all right? It might be, there's a special enzyme that certain people produce that allows them to digest lactose, which is the primary sugar in cow's milk. Now, not every person born has that capability. It's actually kind of weird that we're able to digest another organism's milk, if you think about it. However, a mutation occurred thousands of years ago in Europe and the Middle East and parts of Africa. And this mutation allowed human beings to digest cow's milk. However, you don't find this mutation in Americas. Right? You don't find them in Central and Eastern Asia or in Australia. So people from whose ethnicities come from those areas, they tend to be what is known as lactose intolerant, which means as adults, they cannot eat dairy products. And however, since we know that it's this enzyme that helps digest the cow's milk, you can actually take that as a dietary supplement, as a pill. Let's say you're lactose intolerant and you want to have some ice cream. You can actually take a pill that has this enzyme in it. It gets into your stomach. You can then eat the ice cream or pizza or whatever, and it helps digest it, and it doesn't make you very sick. So that's one example. Another enzyme that we use is in lens cleaner. If you have contact lenses, there's a protein. If you have contact lenses, there's a protein that your eyes secrete that attaches itself to the plastic, or when it used to be glass, of your contact lens, and it causes it to fog over, and so you can't see through it. So they have eye drops and lens cleaner that has this enzyme that breaks down that protein, and that allows the contact lenses to be clean. Kind of cool, huh? So that's what you guys need to know at this point about chemical kinetics. All right. If you have questions, please come to tutorial.